video on some of the rules with radicals, and we're going to start with adding radicals. So if the radicals do not match, if I have, like, for example, radical A plus radical B, I cannot simplify it. It just has to stay as is. But if the radicals precisely match, if I have radical A plus radical A, I can add them together and get 2 of the radical A's. And it doesn't matter whether it's a variable, whether it's a number. If I come down and look at my specific example right here, my 5 radical 3 can be added with, well, or in this case subtracted with 2 radical 3. So these two can be added together. 5 radical 3 subtract 2 radical 3. I am just adding or subtracting the coefficients. So 5 minus 2 is 3 of those radical 3's. And then the other one that doesn't match, that's my unlike radical, I just bring it down and don't change it. Same thing for another example. When I look at this one down here, the bottom example, my 7 radical x and my plus radical x are my only like terms. I'm going to add them together. And again, I'm adding the coefficients. 7 plus 1 gives me 8 of the radical x's. And everything else does not match. The radical y does not match the radical xy. And none of them match the radical 3x. They have to precisely match. So then I would just bring them down, and that would be simplified as much as possible. So addition and subtraction of radicals, just to start out. Some more rules. So we look at multiplication. Anytime that we find it advantageous, we can break a number up if we can break it up via multiplication. So for example, radical 10 could be written as radical 5 times 2 under a single radical. And if I feel like it, I can also say it's equivalent to radical 5 times radical 2. And I can do the same thing with division. If it's advantageous to me, I can say radical 3/4 is equal to radical 3 divided by radical 4. And again, as you become comfortable, you realize when it's advantageous and when it's not advantageous to do that. And you can go back and forth. Okay. So kind of a formal definition of how to simplify radicals is if you can get the index to match the power, they will simplify, and it's just whatever's to that power. Be it a number, be a variable, or even something a little more crazier, a binomial squared under a radical will also, again, the exponent will cancel the index, and the answer is just whatever's raised to that second power. And it can be raised to the third power. It can be raised to any power. And right now we just want to really think about the n being a positive integer. So I don't want it to the 2/5 power or to a decimal power. I just really kind of want to think about it right now as a whole number. So I could say the 9th root of 27 to the 9th power. The 9's will cancel in the index and the power, and it's just whatever's raised to that power. So this all comes from, or is helped out, by realizing that you can write any radical as a base to a fractional power. And the exponent will become the numerator, the index will become the denominator. So z to the 9th with an index of 5 would be written as z to the 5/9. Or I could do a number, 93 to the 4th under a radical with an index of 7 would be equal to 93 to the 4 over 7th power. And the reason why they cancel up top when they match, again, is because you're setting them as a fraction, and any fraction blank over blank can be reduced. So x to the 8th with an index of 8 is x to the 8 over 8. And 8 over 8 reduces to 1, which just gives you an x. Or just plain old x to the first. Now, one way to simplify radicals is if we can get the power, or if we hope that the power is a multiple of the index. So for example, if we have x to the 15th and we have an index of 5, we could think of this as x to the 3 times 5, right, with an index of 5. And the 5s will cross out. So the 5 takes the radical away, and this is just equal to x to the 3rd. Now that may seem super clunky. So some people may actually use parentheses around this. They'll take the x to the 3rd, put it in parentheses, raise it to the 5th power for 5, keep the index of 5, and then the power of the 5 cancels out with the index of the 5, just leaving with an x to the 3rd. You can also, again, write it as a fraction. I could take that same problem and say, let me use this concept, let me rewrite it as x to the 15 over 5 power. This is reducible. 15 over 5 is 3. Again, I get the same answer. If you're still not comfortable, we can look at one more scenario. So most of us know by heart that the square root of 64 is 8. Right? We just know it. Again, our method formally is 64 can be written as 8 squared, and the square and the radical cancel, giving me an 8. We can also break this down using a factor tree. If I break down 64, 8 times 8, if I don't circle these, if I keep going, I can see that I have 6 2's being multiplied together. So 64 is equivalent to 2 times 2 times 2 times 2 times 2 times 2, or easier, 2 to the 6. So now if we look at the square root of 2 to the 6, which is again equivalent to 64, I can either directly rewrite this as 2 to the 6 divided by 2 because of the index. 6 divided by 2 is something that's easily manageable. 2 to the 3rd, and then 2 to the 3rd is equal to 8. I could also rewrite 2 to the 6 as 2 to the 3rd squared. Again, 3 times 2 is 6. The power reduces or cancels. The power cancels the radical, and this just gives me 2 to the 3rd. And again, 2 to the 3rd is another way to write 8. Then the last thing I want to look at is this crazy problem right here. And we're going to take advantage of all the rules that we got. So my first rule that I'm going to take advantage of is that I'm allowed to, again, take factors and break them up into separate radicals. So I'm going to break this up into radical 18 times radical x to the 7th times radical 3x squared plus 5x minus 6 in parentheses to the 4th. But I'm not done with that rule. I'm going to take 18 and I'm going to break it up. Now, we have these nifty little sheets down in the LAC. Kind of a little cheat sheet helping you with perfect squares. I can see that on this cheat sheet, the square root of 9 is equal to 3. Again, showing my formal notation here, that square root of 9 is equal to radical 3 squared, and then the radical cancels with the exponent, and I just get a plain old 3. I can take advantage of that. I can break 18 up into radical 9 times radical 2. I'm going to do something similar for the x to the radical x to the 7th. Here, I want, so looking at this rule that we had, I want the numerator, I want the power to be a multiple of the index, of the denominator. So I want to take this number that's currently a 7, and I want to figure out what is a multiple of 2 that's smaller than 7. Well, counting downward, 7, 6, 5. Let me go back to 6. 6 is a multiple of 2, so I could rewrite this as x to the 6 times x. There's my x to the 7th. Again, just using that top rule to split it up. And then I want to attempt to do the same thing with the last one. I want to look for the last one. I want the exponent to be a multiple of 2. Well, it already is, so I'm not going to split this up. I'm going to keep this the same. Now, 3 of them, 3 of these radicals are perfect squares. Mattering how I want to handle this. Okay, I could say, well, gosh, I just know the square root of 9 is 3. If I just want to get used to the concept, I could write this as radical 3 squared. Cancel, cancel. I have a 3 coming out. The radical 2, can't do anything with. That's just going to come down. But x to the 6 under the radical, that can be broken down. Again, however I want to write this, if I want to do is x to the 6 over 2, and then say 6 divided by 2 is x to the 3rd, I can do that. Or I could do the same radical method just to show you. And then I can cancel those out. So either way, I'm going to end up with x to the 3rd. I have an extra radical x. That's going to join the radical 2 coming down. So I have 2 things that are to be determined, to figure out, or just to write them in. But the last one, I got that 4 here. I got that index of 4. It doesn't matter what it's on. It's on a trinomial, binomial, any kind of object. Monomial, doesn't matter. It's to the 4th power. I know that 4 divided by 2 is 2. So what's happening here is 3x squared plus 5x minus 6 to the 4 over 2 power. 4 over 2 reduces. So it's 3x squared plus 5x subtract 6 squared. And then my to be determineds are my radicals. And here, I'm going to go backwards. I'm going to take my 2 radicals, my radical 2, my radical x, and bring it backwards and put them under a single radical. And this becomes my final answer.